and as we will see, the confinement also in tracks of dot is also important. And so what we have done is first to collect a lot of information of the dialysis-chemo interaction at different types of interfaces. Now there are a lot of data. And then we are beginning some experiment on this sort of multi-layers, not on ultra-thin layer, on this multi-layer. But before, to explore the way, we have developed simulations, micromagnetic simulations that I will explain now. So micromagnetic simulation based on this expression of the dialysis-chemo interaction for a micromagnetic model, with M is as a function of the derivative of M, and the coefficient D is related to the D12 that I have introduced for concrete spins, and of course is supposed to be inversely proportional to the thickness of the magnetic film, of course, dilution effect. And we have collected a lot of information for several interfaces. And what we don't want with this simulation to explore the physics of all the situations with skirmion, but we want to test several mechanisms of nucleation of skirmions and to study the property of these skirmions that we have nucleated. So I will begin by showing the nucleation, then the current induced motion, and then the pinning. For the moment, all the simulations are zero temperature. We are beginning at finite temperature and in general at zero field. To see what sort of skirmion we want to study, I show this the energy of skirmions in dots. This sort of skirmion in dots, you can see the in color scale the configuration. There is always tilt at the edge of the. And this is the energy of the skirmion state, and this is the energy of the ferromagnetic state. And you can see that in this range, the skirmion state is more stable than the ferromagnetic. It's not so interesting for us. The interesting regime for many application is this one, where we have metastable skirmioning states in a ferromagnetic disk, but protected by the topological protection. So this curve is this is D, and D is a relatively small value of D, corresponding to about, for example, D for one monolayer with referring to the work by Wiesenegger, would correspond to a D in this range. So for two monolayers, this corresponds more or less to this value here, about 5. And this value corresponds to 3 or 4 layers of film with 3 or 4 layers, a little less than 1 nanometer. What you can see also is what control. In fact, there is a difference. Okay, I do not show this. Compared to the skirmion lattice, when you have a skirmion lattice and we increase the dialysis-chemo interaction, the system tends to create more skirmions of smaller size. But when the confinement is important, when you have created a single skirmion and that the number of skirmions is fixed, you have not the choice, then the variation of the diameter of the skirmions is different. In fact, when D is decreased, the ferromagnetic state around progressively compresses the skirmion to give rise to smaller and smaller skirmions. It's exactly the contrary as we can see in lattices of skirmions. And on this side, on the contrary, the skirmion extends more and more in the disk. And after some threshold value of D, then one finds the skirmion breaks into several skirmions and so on. Okay. And mainly we want to study this regime, metastable skirmions into a stable ferromagnetic disk or track or stripe. So this, to give you simply an example, that the size of the skirmion can be controlled not only by D, by the DMI interaction, but also by the magnetic anisotropy that is compete with the dialysis-chemo interaction. You can see an example of the size of the skemion as a function of k for different value of d. So nucleation. Nucleation, so we try we tested several mechanisms of nucleation. This one is injecting a spin polarized current, a vertical spin polarized current, into this central circle of the disk. And this spin polarized current has a polarization, a vertical polarization, and so we simply simulate the dynamics of the system by introducing the usual spin transductor that we have seen several times this morning, and introducing the polarization of the injected current. Can be injected magnetic junction, and alpha is the damping coefficients. So first we started with cobalt, for which we know we have several experimental results on alpha, but a relatively large alpha. And then for alpha large, because in fact you know that this is an anti-damping torque that competes with the damping alpha. And then, in fact, when alpha is large, it's not so attractive. Of course, one needs not only a relatively large value to obtain skyrmion by this mechanism, you have to have a relatively large value of d corresponding to, say, two monolayers, to a thickness of 4 or 5 angstrom. And also you need relatively large current density. But in fact, we have found finally that for this mechanism of creation, we need to work with a sample, with field magnetic field, or small alpha, for example, cobalt, iron, boron, with this sort of value of alpha. And then it's become possible to create a skemion with reasonable current density, less of the order of a few 10 to 7 amps per centimeter square. In fact, it appears also that this can be done not only with a vertical polarization, with also horizontal polarization of the injected currents. The physics is interesting. So the interesting physics in this problem is how to cross a topological barrier that in principle protects to go from one side to the other side. And so I want to illustrate this process by some image during the creation of the skyrmion. So the first state is a ferromagnetic disk. This represents the DMI energy density. So its ferromagnetic state is 0 except at the edge, due to the tilt of the spin by the Dialog-Schmidt-Kimura interaction at the edge. Then the first stage is the creation by spin transfer of a bubble. Right? A bubble, but this is not a skyrmion. The first stage is not a skyrmion. It's a bubble. You can see that if you look at the rotation of the spin, the rotation is clockwise here, and then anti-clockwise on this side when one goes along this line. You can see also, if you look at the DMI energy, on this side, there is a negative energy that is chirality agrees with the sign of the DMI, and on this side disagree and increase the energy. So it's not is a bubble, hard bubble. In fact, and in between, there is a sort of two domain walls with opposite chirality on this side and on this side. This corresponds to the scheme for bubbles, a classical picture for bubble, hard bubble, with different chirality for the domain walls on both sides, and in the middle, at this point, what was called a block line. Block line, because in fact, with the bubble, the thickness was not so small. And in fact, the next step is that progressively, with the Dialog-Schmidt-Kimura interaction, the part of the domain wall, of the pseudo-domain wall, in agreement with the Dialog-Schmidt-Kimura interaction, progressively compress the other part into this small defect of very large energy exchange and DMI energy. So this, but still, S is still equal to 0. We have no skyrmion, so we have, and then S is still 0. And then this is the equivalent of what in the language of the Burl was a block point. In fact, in the language of bubble, it was possible to compress also the block line into a block point, and it occurs the same mechanism that in bubble, that at some stage, after some time, then suddenly this defect explodes. There is explosion of defect, emission of spin waves, and then S goes to 1, and progressively the system is stabilized into a skyrmionic state like that. And so this explains the difficulty. So in fact, I want to mention this similarity with what was known for magnetic bubbles, and also what was known. Of course, these simulations are not realistic in the last stage, because it was necessary to reduce the dimension of the mesh to very small size to study the last stage of the explosion of this defect. But it was the same situation in the physics of the bubble, and one knows that in the bubble, in fact, the annihilation of the block point was always made easier by defects, and so it is certainly the same thing that can be played with the skyrmions. So in fact, there are already experimental results in the group of Wyss and Danger in Hamburg, where in a barrier of palladium ion, by sending an electrical current from the tip of the STM, they are able either to write a bubble at some points, or by changing the condition, changing the field, and dilate this bubble. So there are already experimental examples of this sort of creation of annihilation. What also is interesting to see in the results of this paper here, that this creation is always easier on some defect of the magnetic layer, some adatom or vacancy, and so this confirms that the defect can play an important role to lower. In fact, when you have a topological barrier, if there is some defect, that means that the path is lower at some point. And so certainly this is an example. In fact, we are also making now simulation by introducing defects, some cuts in the magnetic field, and it appears that we are just patenting this mechanism. It seems that by cutting the film with a very sharp shape is possible simply by passing the current through the film to create at some points on these cuts skyrmions. And this has been, we can see example of this sort of mechanism in some Japanese paper recently. In fact, this is also something maybe the next speaker will say, will speak about this. It seems the other mechanism that we are trying, and apparently we begin to succeed to create skyrmions, we have to check that they are created skyrmions, is that by sweeping back and forth several times the field is possible. The idea was at the end suppress or select only the bubbles that are skyrmions. And apparently, I suppose that the next speaker has more or less the same conclusion in some sweeping the field for this cobalt ion layer on platinum. They see an intermediate state that, according to their simulation, they identify to this complex structure that breaks into small bubbles, and in this paper, the paper say breaks into a deformant skyrmion lattice. So it's not clear completely, but it seems that there are several examples now that you can create also skyrmions in this sort of sweeping the field. Okay, so the motion, current driving motion of skyrmions. So we try in-plane current and vertical injection of a spin vortex current, mainly by spinel effect. And so this is the classical expression of the torque, adiabatic torque with an anti-damping torque, and non-adiabatic, which is a field-like. And for the vertical injections, we have, as has been you have seen in the talk by Bob this morning, this anti